everyone, welcome back. Last video we reviewed some concepts from Calculus 1 and Calculus 2. So now let's start numerical methods. Yay! So chapter 2, our goal is to find zeros of nonlinear functions. Okay, so do you still remember how to find zeros of a function? For example, how do you find 0 of like 3x minus 2? Well, you set it equal to 0, right? And then you solve for x. We move the 2 over and divide it by 3, right? This is a linear function. And how do you find 0 of quadratic function? Like a 3x squared plus x minus 1, something like that. How do you find it? Okay, you probably can use the quadratic formula, right? 2a and then negative b plus or minus b squared minus 4ac, but c is minus 1. So something like this, right? So let's see, this is square root of 13 over 6. Okay, so we get 2 roots. How about polynomial? Well, polynomial, we have the rational root theorem. So rational root theorem can help us to find some rational roots. But in general, how can we find 0 of a nonlinear function? What happens if my root is not rational? Okay? So we see questions like, what is the approximate value for cube root of 2? Well, this is the same as to solve, okay, let's say x is cube root of 2 is the same as x cubed equals 2 is same as to solve, to find the root of the function. Okay, so it's the same as to find, the zeros of the function y equals x cubed minus 2, right? And next question is, where do e to the x and y squared intersect? What is this question? E to the x exponential function look like this, and then this is a parabola, right? So parabola look like this. How do we find the intersection points? Well, it's the same as we find the 0 of the function e to the x minus x squared. Okay, so all these questions we can conclude that it's the same as to find the 0 of a non-linear function. Okay, so in this chapter we're gonna talk about different methods to find zeros of a nonlinear function. The first method is the bisection method. So bisection is a systematic search technique for finding a 0 of a continuous function. The method is based on finding an interval in which a 0 is known to occur. Divide the interval into 2 equal subintervals and determine which subintervals contain the 0. Okay, so for example, we have, this is a to b, right? Let's say f of a is negative, and let's say f of b is positive, right? So if our graph look like this, we want to find this 0. So how we do it is, each step we cut the interval into 2 equal size subintervals, right? And then at this point we can evaluate f of m. So if f of m is positive, then we know the roots must be in between a m, right? And then we cut it into half again, and then we evaluate. So we realize, oh, f of this number is negative, then we know the roots must be inside this subinterval. So each step we cut the interval into half. Okay? So let's see, here are the steps. Suppose an interval AB has been located, which is known to contain a 0. Since the function changed signs between A and B, so we know this is by the intermediate value theorem, right? We just talked about that in the last video. right? If f change signs between two numbers, then there must be a root, okay, between the a and b. Then the approximate solution is the midpoint. Okay, so each step we have the approximation. The first step, the approximation, is the midpoint. Midpoint is a plus b over 2. Okay, then a 0 must be line must be lying in either AM or MB. Then the appropriate subinterval is determined by testing the function to see whether it changed signs on AM. If so, the search continues on that interval. Otherwise, it continues on MB. Okay, so we plug the number into our function value to test whether it's positive or negative to determine which subinterval that we proceed. Okay. So let's look at the first example. We consider the function y equals x squared minus 3. Well, when we find the roots, we know this number, the root is going to be square root of 3, right? Okay, so now let's see. So for this kind of problem, I strongly suggest you draw a big long interval. Okay, and in this case, what is our A? A is 1, B is 2. So far so good. So we have 1 here and 2 here. And then we're gonna draw a table, right, everybody? So the bisection method, we're gonna draw the table. So we have steps. So steps very important because each step we're doing the iteration. So each step we have to figure out what is our approximation. Okay, and we have the A and B, and then we have the M. We have the YA and YB and YM. So far so good, everybody? Okay, the first step. A is 1, B is 2. Well, M is the midpoint, so A plus B over 2. So in this case, 1 plus 2 over 3, 1 plus 2 over 2 is 3 over 2, 1.5. Okay, what's YA? YA is 1 square minus 3, right? 1 minus 3 is negative 2. YB, 2 squared minus 3 equals 4 minus 3, which is 1, right? YM, what's YM? 1.5 squared minus 3, that equals, let's find our, okay. This is our calculator. Okay, so let's see here. Okay, so what are we doing? Let me move it here. So we have 1.5 square and then minus 3. The answer is minus 0.75. So far so good, everybody. So this is the first step, right? And on this interval, we find the midpoint is 1.5. Okay, so f of 1 is negative, so we put the negative sign here. F of 2 is positive, we put the positive sign here. F of 1.5 is negative. Okay, then which subinterval we're gonna continue? We're gonna continue. Oh, look at this, right? Because they're of different sign. So this is our new interval. So step 2, our A is the left hand point. The left endpoint is 1.5. The right endpoint is 2. So far so good. And what is the midpoint? Oh, what happened? Okay. What is the midpoint? What's the midpoint of 1.5 and 2? Well, that's 1.75, right? Is that okay, everybody? So M is 1.75. YA is f of 1.5, but it's the same. This is we calculated before, so we don't need to calculate again. Let's copy it down. So that is minus 0.75. And then YB, what's YB? B is 2, so YB is this guy. Is 1. So each step you only calculate the new number is y of so f of the midpoint. Okay, so this is 1.75 squared minus 3, and let's see what is that. Okay, I can teach you a good way to do it. And what is the good way is first you type 1.75, then you click enter, right? And then we can do answer square minus 3. See? You can do it in your calculator. Then enter. So this is the f of 1.75. So it's 0.0625. Okay, 0.0625. So far, so good, everybody. So this is positive. See, this is positive. Now, which subinterval we should choose? This guy. Right? So the left endpoint, so this is the third step. The left endpoint is 1.5, the right endpoint is 1.75. And what's the midpoint? Well, what's the midpoint of it? Well, okay, let's see. So the answer is 1.625. Is that okay, everybody? Yes, so this is 1.625. You can use 1.5 plus 1.75 and then divide it by 2. Okay, YA, because the left hand point is still 1.5, so this is still minus 0.75. And the B is 1.75, and then we have this 0.0625. Move it here. Okay, and then we want to calculate f of 1.625. Let's come back to our calculator. So we can type 1.625, enter, and then you can go up using this guy. Let me see. Oh. Okay, it's not like my real calculator. So for my real calculator, after we enter this, I can go up to my my previous line, and when I put enter, then I will have the new answer square minus 3. But here I can't. Okay, then we just do it again. So answer square minus 3. But for some of you, if you have your actual calculator, you can actually go back to your previous line. Then you don't need to type it again. Okay? So the answer is negative 0.359375. So this is 1.625 squared minus 3. And this is negative 0.359375. So far, so good, everybody? Okay, and this is negative. Then which subinterval we should continue? Oops. This guy, right? The left endpoint is 1.625. The right endpoint is 1.75. And then the midpoint. Okay, what is the midpoint? Okay, so here, let me use our calculator. So that is parentheses 1.625 plus 1.75 close parentheses, divided by 2. That is 1.6875. 1.6875. So this is, whoa, okay. This is 1.6875. See, that's why I asked you to draw a long enough interval. Then you can be able to see where's the midpoint. All right. YA, f of 1.625 is this negative 0.359375. F of 1.75 stay the same. 0.0625. And then we have this 1.6875 squared minus 3. And let's see, what is that? Okay, so we already have that answer. So we have answer square minus 3. Negative 0.15234375. Negative 0.15234375. So far, so good, everybody? Okay, this is negative. Oh, so this is negative. What is the subinterval? Well, this guy, right? So this is, let's say this is our last step. So the left endpoint is 1.6875. Right endpoint is 1.725. And then the midpoint, oh, let's see, what is our midpoint? We use 1.6875 and plus 1.75 close divided by 2. 1.71875. So 1.71875. Okay, so here 1.71875. Okay, YA is this guy, negative 0.15234375. And then YB, stay the same. Okay. So when you do this table, it is enough to keep, let's say, 5 or 6 decimal places. Okay. And then YM, this is 1.71875 squared minus 3. And what do we get here? So this guy answer square. And then minus 3. Okay, negative 0.0458984375. Okay, negative 0.4. Okay, let me. I don't have enough space. Let me put it here. Negative 0.0458983 A43 is it 75? Let me see. Sometimes I forget. 0.4589844375. Yep, okay. So this is the 5-step bisection methods. And what is our approximation? Here. So after 5 steps, this is our approximation. So far, so good, everybody? Okay, then we can say the approximated zero is the approximated zero is 1.71875. Okay, so here we can actually use MATLAB to use the bisection method to compute this example. And this is the table we get. And let's see, we get to the 5th step, right? You can see our estimated 1.7188. Yeah, that matched with our answer. So the MATLAB usually it keeps 4 decimal places, but you can also change the preference, okay, to have more decimal places. And ym, this is the ym, and here this is our ym. So far so good. And it also has the error bounds. Okay, so far so good. We can also graph this function. So this is the function x squared minus 3. Well, you know, x squared minus 3, x squared is a parabola, open up. So minus 3, we move 3, right? So this is the parabola, and then we can use GeoGebra or any other software to sketch the graph. And this is the graph. You can see the zeros is somewhere between 1.5 and 2, and our approximation 1.71875 is close to this true value. Okay? Alright. Noticed. From the ym column, the values of the function at the approximate zeros. It is possible to be quite close to the true zeros at some stage of the iteration, and then move away from the zero before returning to a good approximation later. We can see that we have a better approximation at step 2 than step 3 and step 4. So yes, let's look at this. You can, let me use a different color. Okay. So this is ym. We know, because we're looking for the 0. If the y is close to 0, that's good, right? And you can see 0.75 not so close, and 0.06 is quite close to 0. But 0.35 is not so close as the 0.06. Right? So the second step, we get a better approximate than step 3 and 4. But actually, when we continue to do this process, eventually, we will get a closer and closer estimation. Okay, but it is possible that at some stage, maybe the approximation is better, and then we move away from it a little bit, and then we will get back later. Okay? Second, the bisection method provides a bound on the 0 at each stage of the iteration. At each stage, the distance between the true 0 and the computed 0 is no more than half of the length of the current interval, right? So we can draw the picture here. So here we have A and B, right? And then this is the midpoint. Is A plus B over 2. Okay, so at the first stage, okay, let's say this is the stage. At the first stage, the length of the length of the interval is b minus a. Then our estimated 0 is the midpoint. Okay, so the bound at the first stage, our estimated 0 is at most within b minus a over 2 to the true 0, right? So no matter the true 0 is here, then you can see that the distance is within b minus a over 2. Or it could be here, then the true 0 is still within b minus a over 2. So far, so good, everybody? Okay, how about the next stage? Well, second stage, because we cut it into half. Let's say if we pick this interval and we cut it into half again, then the bounds will be b minus a over 2 squared, because we cut it into half again, right? So at each stage, the length of the interval is halved. So the maximum possible error is reduced by a factor of 1/2. So at step K, so we continue until we reach step K. Then the error bound is b minus a to the 2 to the power. So b minus a over 2 to the power of k. Okay, so this is the error bound. So far, so good, everybody? Okay. Example 2. Suppose the bisection method generates a sequence of approximations xn using a starting interval -1, 3, give an error bound for the 5th iterate. Okay, so keep in mind that when we use bisection method, the error bound for kth iteration is b minus a over 2 to the power of k, right? Oh, okay. And then, so we're looking for the 5th. So we plug in k equals 5. And what is our interval? Our interval is from -1 to 3. So we plug in a is -1, b is 3. Then the error bound, okay, so the error bound is b is 3, minus a is -1, 2 to the k is 5. Oh, so the top is like 4 over 2 to the 5th, right? Well, that's the same as 1. So 4 is like 2 squared. So we're only left with 1 over 8. Ooh, that is 0.125. So far, so good, everybody. So this is our error bound. Let's continue. Okay. Example 3, determine the minimum number of iterations of the bisection methods needed to approximate the unique zeros of a continuous function f of x known to exist in the interval -2 to 1 to within 10 to the -4. So here we can have two directions. All right, we can have we know this is let's say we know the number of iteration, and we want to find the bounds, the error bounds. Or we want to control the error, okay, and we want to find the number of iteration. So we have two directions. The previous example is we know we have 5 iterations and we want to find the error bounds. But here we are doing the opposite direction. We want to control the error to be within 10 to the -4. And then we want to find the number of iteration. So far, so good, everybody. So here a is -2, b is 1. So then the error bound, okay, for the kth iteration is, so b minus a over 2 to the k, b is 1, a is -2, 2 to the k. So this is 3 over 2 to the k. We want to have this error to be within 10 to the -4, and we want to solve for k. So how do we do it? Well, both sides multiply by 2 to the k. We get 3 less than equal to 10 to the -4 times 2 to the k. And then both sides multiply by 10 to the 4th. And we get 3 times 10 to the 4th. And then on the right hand side, 10 to the -4 cancel. Just get 2 to the k. Right? Let's switch them. So my unknown is on the left. Okay, how do we solve for k? Well, we can both sides take the ln, so ln 2 to the k greater than or equal to ln of 3 times 10 to the 4. And you know what? We can move the k down in front. So now we get, so this guy is like k ln of 2, right? And ln of 2 is positive. So guys, be careful. This is the ln of x. And this is 1. If whatever you plug in the ln is greater than, so if your x is greater than 1, ln is positive. When your x is less than 1, your ln is negative. When you multiply both sides of an inequality by a negative number, that will flip the inequality. So be careful with that. Here, ln of 2 is positive, so we can both sides divided by ln of 2. So far, so good. Okay, what is this number? Calculator, where is our calculator? Right here. So we have ln here, ln here, ln of 3 times 10 to the 4, close parentheses. Oops. Let's see. Okay. Alright. Okay. Close the parentheses. And then divided by ln. So, ln of, go back. ln of 2. Close the parentheses. Okay, enter. So the answer is approximately by 14.87. Remember, k is the number of iterations, so it must be a whole number. Well, and it must be a whole number that is greater, equal than 14.87. So the minimum k is, we pick 15. Okay, let me ask you a question. Okay? So we mark here. If we get k is greater or equal to 14.01, what do you pick? The minimum k. You cannot pick 14 because k has to be greater or equal. Okay? So this is not like round up or round down. You must round up. Okay? If k is greater or equal to 14.01, then we still need to pick k is 15. Is that okay, everybody? Yes. So always round up, no matter, as long as we have some non-zero digits here, we always round up. Okay, so this is the bisection method. Next, I want to teach you how to use MATLAB to compute. Okay. So here is the script of the bisection method. The process stops if either the first magnitude of the function value at the current stage is less than the tolerance, okay, or the maximum number of iteration k max has been reached. How do we get those scripts? Go to our course website. This is my fall semester link, but it's okay. You in Blackboard, or you just Google to search Suyun Math. Okay, let me teach you from the beginning. Just Google search Suyun Math, and then the first one is me. Okay, so usually you will see the course I'm teaching, and you can see pictures about me and my family and with my students as well. Okay, and so I'm still preparing our course websites, but here down the worksheets you can also find our MATLAB M function folder. Then you just click it, and then it will and then you can download all these M files to your personal computer. Okay, so those are the M files. And then do you have MATLAB at home? So if you don't have MATLAB at home, I suggest you to download Octave. So Octave is very similar to MATLAB. They use the similar codes. In our course, all the codes also work in Octave. Okay, and it is free. So because I'm at home with my personal computer, so I just download Octave. Okay, I forgot my license for the MATLAB. I have MATLAB in my office computer and my classroom computer. Okay, laptop, but here I don't have it. So I just download it, and this is the Octave. So far so good, everybody. Let me make it bigger. Okay, so this is the Octave after you download it. So each homework assignment, there will be some homework problems require you to use MATLAB to compute or Octave. Okay, so first, do you remember you download the M function files? So the file browser usually doesn't, when I download it, I just see it starts with like a Yunsu, and then I go to my Google Drive because that is where I store my M function. Okay, and this M functions. Then so you have to open the folder of M functions. Then you can calculate the code. So far so good, everybody. All right, now. Yeah, so after you download all those files, remember to unzip it, okay? Extract the folder. And open MATLAB. Make sure on the search path, the current folder contains all the M functions files. So this is what you see in MATLAB. Okay, I print screen it. Okay, look at this example. Use bisection method to find the zeros of this function on the interval 0 to 1. So we can use GeoGebra or any graphing software. We can graph the function, and it looks like this. So you can see from this picture, you can see we have a 0 between -2 and 0. We have a 0 between 0 and 2. And we have a 0 that is bigger than 2. So far, so good, everybody? Okay, so how can we find all 3 zeros? Well, the syntax is brackets m, ym, brackets, equals capital B, bisect, okay? Bisection method, bisect. Parentheses, f is our function, a is the left endpoint of the interval, b is the right endpoint of the interval. Tolerance is how how small you want your answer, so the y value is gonna be, okay? So you want to be very close to 0, right? So that's why you can put your tolerance is 0.00001, okay? Then the function value at that point, the estimated 0, should be smaller than 0.0001. And K-max, that is the number of iteration. Okay, so let's type 10 in this case, 10 iteration. Okay, so keep this in mind. So we're gonna input, so for functions, you're gonna input inline and then parentheses is called single quotation mark, x dots, okay, to the 3. Okay, this dot is, you need a dot when you have a vector, okay? So x is usually when we type x in it, the MATLAB assume it is a vector. So if you want to use the pointwise multiplication, you can put a dot there. But because in this session we're not working with vector, so if you put a dot or you don't put a dot, doesn't matter. But in the later sessions, when we talk about vector value function, then if you want to have a pointwise multiplication or pointwise power, then you have to insert the dot. Okay, and also if you want to plug in 3 times x, you have to put 3 asterisk x. Okay, if you don't insert the asterisk, then the MATLAB just consider 3x as one variable. It's not like 3 times x. They just consider 3x is a single variable. Okay, so keep that in mind. Oh, by the way, this is what happened if I plug in MATLAB, and you can see I get a table, I get steps 1, 2, 3, 4, 5 to 10, and I get A, B, M. M is like the midpoint in each stage. YM is the Y function values at the midpoint, and we also have the bounds. Okay, and here you see 0 not found to the desired tolerance because our YM is negative 0.0016, but our tolerance is set to be 0.00001. Okay, so that's why 0 is not found in the tolerance. But you can increase the number of iterations. Okay, we can increase the number of iterations. You can do 100 steps or 1,000 steps. Eventually, we will get the desired tolerance. Okay, so let's put that in. Okay, so let's put that in Octave. So have you downloaded Octave? I hope everybody can try it with me. So Octave here. Let me move down a little bit so I can see it. Okay, everybody. So yeah, here bracket. Oh, let's see. Bracket y comma ym equals bisect inline parentheses single quotation mark x squared x cube minus. So actually I calculate in the previous step, but I forgot to do x squared there. So that's why you see I got a different answer. So x squared, so don't forget square this time, and then plus 1. And let's say we're looking for the root. You see, from this picture we have 3 roots. One root is between -2 and 0. One root is between 0 and 2. Another root is between 2 to 4. So let's find the root between 0 and 1. Okay, tolerance 0.00001. K mass number of iteration is 10. So let's see. Oh, you see I typed the wrong thing. Okay, it's okay. Let me fix it. So I mean asterisk. Okay, here it is. So even though the columns doesn't align so good, but it still worked, right? You can see this number. Let's see, 0.6533. What do we have here? Yes, 0.6533, and it has more digits. Good. You see? And still zeros found, not found to the desired tolerance. But then we can increase the number of iterations. Let's do 100. See, at the 7 steps, the bisections converge. Okay, so this is the root. 0.6527 is the root between 0 and 2. Let's put it down. So we know that root is 0.6527. Let's try to find the other 2 roots. Okay, this one, let's try -2 and 0. Okay, so you just here you just press the up arrow, then you can go to the previous line. Here I want to find the roots between -2 to 0. And so far so good, everybody. Let me see, can I I cannot make it bigger. Sorry, I cannot make it bigger. Are you able to see it? Let me see. It's still not bigger. How can I zoom in here? Is any like view button? Can I view or zoom in. Okay, no, but please keep that in mind. You can try it on your screen, okay, your octave in your computer. Okay, so let's enter. So we have the bisection method converge, and our answer is negative 0.5209. Here negative 0.52, I forgot, 53209. 53209. Okay, we can also find this bigger root. This root is between 2 and 4, I would say. So see, 4 is like here. So let's do it. So we go up and change from 2 to 4. And then, so the roots, the estimated 0 is 2.8794. 2.8794. So now we have find the 3 roots. So far so good, everybody. And I also want to tell you, that's why we need the knowledge from Cal 1, because it can tell us like what's the shape of the function and how many roots there is, right? So let's see here. Well, this guy you can see here, because the function is increasing, we know on this interval there's only 1 root, and on this interval, because the function is decreasing and I've changed signs on the endpoint, we know it has 1 root. And on this piece is also increasing, and I've changed signs, so it also have 1 root. So altogether, you can see there are 3 roots for this function. So far, so good, everybody. Okay, so that is the bisection methods. And furthermore, you know what? The good thing about examples from we did, okay, the bisection method, we can always check our work. See? So we can check our work. We can type in, let's see here. Let me make it smaller. We can type in, we don't need to type it again, so just go back, and here let's do what is our function? Our function is x squared minus 3. Right, x squared minus 3, and the interval is from 1 to 2. Okay, and we enter it. Oh, we get to the 5th set. So the m is 1.71875, and this is my ym, and you can see it matched with our answer. So after you finish your homework, for this kind of problem, you can check your work, right? And then if you see a mistake, and then go back and check it. Okay, you can see it gives you an answer from each step, so then you can find your mistake easily. So far, so good, everybody. Yeah, so in your homework, you're gonna have some problems. You first do it by hand, and then you can use MATLAB or Octave to check your work. And also you're required to print screen, so you can use the snipping tool in your computer, and then you can just capture some screenshots and then paste on your homework, and then you can turn it in. Okay, convergence. So for iterative process which produce a sequence of approximations to the true solution of a problem, it is important to know whether or under what conditions the sequence converges to the true solution. If so, how rapidly? We describe by using the order of convergence and the rate of convergence. So if for some lambda greater than 0, if the limits of the absolute values of the difference between the true value and this is the approximation in the k plus 1 step. Okay, so if this guy divided by the true value minus the approximation in the k steps, okay, to the power of p equals lambda, well, it's the same as, but because when k goes to infinity, well, this means we can both sides multiply by the absolute value of the true value minus xk to the power of p, but if you don't write the limits, we will get approximately equal to. Okay, or we can have less than equal. So they're the same thing. Then we say the sequence xk converges to the true value with order p. So p is in the order, in the power. Okay, and the number lambda is called the asymptotic error constant. It's also called the rate of convergence. And if a sequence converges with order p equals 1, we say it is linear convergence. Okay, everybody? So, and in general, the order of convergence dominant, okay, than the rate of convergence. Okay, so we first look at the order. If the order is big, then the convergence is faster. And then if they have the same order, then you look at the rate of convergence. If the lambda is smaller, then it converges faster, because it's talking about the error bound, right? So example 5. Suppose an iterative scheme is known to converge with order p equals 3, and the asymptotic error constant lambda equals 0.7. If E0 equals 0.6, estimate E1, E2, E3. So we use the true value minus xk plus 1 is approximated by lambda x, the true value minus the k set to the power of p, right? And here p equals 3, lambda equals 0.7. And lambda is a number that is smaller than 1, because you want your error to be smaller, right? Okay, so we have true value minus xk plus 1 is approximately 0.7, and true value minus xk to the power of 3. And if we call this guy is the error in the k plus 1 stage, this approximately by 0.7 times error in the k steps to the power of 3, right? And E0 is 0.6, then E1 is approximately 0.7, and then we have 0.6 to the 3. Oh, let's see. What is this? Calculator. Where is my calculator? Here is my calculator. Okay, so 0.7 times 0.6 to the 3, and 0.1512. Okay, how about E2? Well, E2 is then 0.7 times E1. So E1 is 0.1512 cube, right? And that equals, calculator, 0.7 times, we can do answer. So answer to the 3. Okay, so, well, that is point. Oh yeah, sorry, I forgot. 0.0024196548. You have that in mind? Okay, what is it? 0.002419, and then what? 65481. 65481. 65481. So far, so good, everybody? Okay, how about E3? Well, E3 is then 0.7 times, that number, long number, cube. Okay, where's my calculator? Here. Let's see. Can I go back and enter? Oh, I can't enter it. But with your calculator, with your actual calculator, you can go back to the previous line and just enter it again. Then you have the new answer. But here I need to type it again. Okay, answer cube. Okay. Ooh. So 9.916. Let's do 9.9165. 9.9165 times 10 to the negative 9. Okay. Well, such a small number. See? Yes. So actually, that's why the order of convergence really matters. If you have a bigger order, the convergence is gonna be much faster. Okay, so what do I say? Okay, let me see here. Let me do a remark here. Okay, first one, let's say the order is 5 and the lambda is 0.8, and then the second one, p is 3, the lambda is 0.1. Which one converge faster? Of course, the 5 one converge faster, right? Oh, let me do one more. Okay, who's the fastest? Here, this is the fastest. Because the 5 is a larger order. So, if the order are different, then whoever the bigger number of the order, that converge the fastest. And then if these two, if the order are the same, whoever constant is smaller, okay, then it converge faster. Let me see. Okay, can I say this is the number one fastest, and then this is faster, and this is the slowest. So far, so good, everybody. Yeah, the order is like that. Okay. So this is the convergence, the order of convergence and the rate of convergence. So far, so good, everybody. Okay, and so don't forget, if you have any questions, you can always print screen and then ask me in class or in office hours or email. Okay, have a nice day. Bye.